So, welcome to the next lecture on signals and systems, and we proceed with our discussion of the Fourier transform. Well, it has been our practice in instruction to gradually involve the students sitting in front of us in the process of learning. And now that we are almost 1 month into the course, we have had a number of lectures and the students have been familiarized with the setup. It would be a good idea to call them occasionally to the stage to try and gauge their understanding of the subject discussed. So, today I shall call Nikhil to summarize what we did in the previous lecture.
Well, hello everyone. In the last lecture we continued with our discussion on Fourier analysis, and we found that we can express any continuous function xt which is either periodic or which is non-zero for a fixed interval in time in terms of a set of orthogonal basis vectors e raised to k into j omega naught t. And we also devised the notions of the dot product and the modulus for these set of orthogonal vectors, and then we found the exact expression for the coefficients of the various basis vectors for any xt. We even found out that if we know the impulse response of any LSI system, we can use that to find the output of any e raised to j omega naught t, and then by using the properties of the LSI system, namely the linearity and the time shift invariance, we can find the exact response to any xt expressible in this form to get the corresponding yt. And lastly, we also found out that if we give an periodic input xt to an LSI system, the output is also periodic in time. That is basically the summary of the last lecture.
Very good. Very good. So, that is a reasonably comprehensive summary. Would anybody like to add anything to it or subtract something from it? Well, a couple of points that I would like, I think Nikhil has made a very thorough summary. I'd like to add a couple of points to the summary. One is that towards the end of the lecture, when we proved that, applying a periodic input to an LSI system results in a periodic output, it must also be stressed that the period is the same, right? So, the output of the LSI system has the same period as the input. That must be stressed, yeah. In fact, after the previous lecture, one of the students came to me and pointed out a very interesting relaxation of this condition. In other words, do we really require both linearity and shift invariance for ensuring that when we apply a periodic input to a system, one gets a periodic output with the same period? No? Would you like to come and explain? Come.
So basically, when we derived that, we never used shift invariance anywhere. All we did was took the Fourier transform, multiplied it to get the impulse response to get a y of t. So even if the system is only linear, we'll get it periodic with the same t.
Okay. Well, that's not quite correct, because when we said that applying an e raised to the power jk omega naught t to the system results in a multiple of e raised to the power jk omega naught t, we were implicitly using the LSI property. The way when we talked about the Fourier series representation, we did, the way we reasoned it out, actually we didn't really arrive at this conclusion directly. We first looked at the output of the system to a Fourier series input, and we said that if you apply a Fourier series, the output also can be expressed in a similar kind of Fourier series, and that's how we noticed this property. But later we proved this periodic input, periodic output property by looking at the convolution relationship of an LSI system. Now, it's not really correct to say that for a system that is purely linear, if you put in e raised to the power jk omega naught t, you get e raised to the power jk omega naught t coming out. I'll give you an example to, a counter example. Suppose we have the following system: yt is t times xt. All right. Now this is a linear system; it's not shift invariant. But when we put in e raised to the power jk omega naught t, we get t e raised to the power jk omega naught t. Right, and this is not a multiple of e raised to the power jk omega naught t. This must be noted. Yeah. So you see, it's very important to see linearity and shift invariance are required when we make a statement that e raised to the power jk omega naught t, that is a complex exponential, results in a multiple of the same complex exponential at the output. But my question still holds. Do we need to use both linearity and shift invariance in assuring ourselves that when the input is periodic with period t, the output is also periodic with period t? Right. So in fact, my hint to you, any other opinions on this? That's right. Would you like to prove that? Prove that. So it's very interesting. Nirmesh says that shift invariance alone would guarantee that periodicity at the input results in periodicity at the output. So would you like to prove it? Yeah. Erase this. Yeah. Use this and erase this first.
One is what we are given. That is, the input is periodic with period t. So after this, we have to show that the output is also periodic with the same period. We apply shift invariance to s of xt plus t. Since this is the same as xt, so the output will be the same, only shifted by a time t. Therefore, output will be the same as what it was originally, only shifted by the time t. Therefore, it will be periodic.
Very good. Very good. A little, I think, his proof is along the correct lines. I think he didn't state some of the part of the proof correctly. See, the proof is that for a periodic input, xt plus t is equal to xt. That's by definition what we mean when we say a function is periodic, right? Now, obviously, since these two are equal, the outputs of the system are equal to them. So then the system, what he is saying is that if the system is if system S is shift invariant, only shift invariant, we are not asking for linearity here, right? If the system is purely shift invariant, then of course, because these are identical, their outputs are going to be identical, but let the output to this be yt. Now, in a non-shift invariant system, we can't say anything about, the output corresponding to xt plus t in terms of yt, but in a shift invariant system, the output corresponding to xt plus t would be yt plus t, right? So, therefore, from this equality, yt plus t shall be equal to yt. That means the output is also periodic with the same period. Okay? So, it is very interesting. Actually, as Nirmesh points out, the shift invariance property is sufficient to guarantee that a periodic input with a period t results in a periodic output with the same period t. All right. So, it's very interesting. It really means that, if to a shift invariant system we give a periodic input whose Fourier series can be obtained, then the output can also be expressed in terms of a similar Fourier series. And this is true for systems that are only shift invariant. I mean, they could be linear, there is no problem, but even if they are not linear, such a property holds good, right? Now let us go further in our discussion of the Fourier transform. You see, in the previous lecture, we concentrated our attention on the Fourier series, right? The Fourier series, in fact, what is the difference between a series kind of representation and a transform kind of representation? In fact, we haven't brought in a transform formally as yet, right? We haven't brought in a transform formally as yet. We are still proceeding in that direction. But I thought we should look at our coordinates at some point in time. You see, what is a series? A series is a collection of terms which can be put in one-to-one correspondence with a set of integers. What is a series? I repeat, a series is a mathematical expression with terms, or with a sum of terms. Well, it could be a sum, it could also be any other operation. Very often we refer to a sum of terms which can be put in one-to-one correspondence with a set of integers. So, for example, take the Fourier series representation, right? It is a sum of terms of the form Ck e raised to the power j k omega naught t, where omega naught is 2 pi divided by t. So, summation on such terms here. Now, of course, naturally this set of terms can be put in one-to-one correspondence to a set of integers, because you are summing over the set of integers. Yeah. Now, we restricted our discussion in the previous lecture to inputs that were either periodic or which had an existence on a finite interval of time. Yeah, which had an existence on a finite interval of time. Today we wish to carry the discussion further. Suppose we wish to accommodate arbitrary inputs, right? How do we go about it? Now, you see, the first thing that we need to understand is that the answer to some extent lies in what we saw was the effect of the system on the Fourier series last time. Let us look at it once again, but from a slightly different perspective, right? From a slightly different perspective. So, we said if I put into the system a periodic input, by the way, I must again use the word of caution. See, I said most reasonable periodic inputs would be amenable to a Fourier series representation. That means they allow you to expand in terms of a Fourier series. But there are some pathological cases. I am sort of postponing the discussion to what are the actual requirements towards the later part. First, let us look at the positive side of the story, and then we will come to the negative side, right? So, we will at the moment assume that the inputs that we are dealing with, if they are periodic or if they are on a limited interval of time, do have a Fourier series representation. That means the Fourier series converges to the function in question. Now, there are some pathological cases where this will not happen, but we will see them later. I think it is better to see them after we have an experience of the Fourier series. So, going back to our discussion last time, we said if we put in summation Ck e raised to the power j k omega naught t into the LSI system, with impulse response ht, what comes out is summation on k Ck. Now, I will rewrite this in a slightly different way, Ck times h with omega evaluated at k omega naught e raised to the power j k omega naught t. So, you see, it is like this. We said we could define a quantity capital H of omega on the system, LSI system. This capital H of omega we saw last time was like a dot product. It was the dot product of ht on e raised to the power j omega t. We gave it that interpretation last time. We said it's like a projection of the impulse response on e raised to the power j omega t, on a complex exponential of frequency omega. So it's like the component, in one sense you might understand this as a component of the impulse response on the frequency omega, so to speak. Right? It's like taking the projection of the impulse response on a complex exponential of frequency omega. Of course, please remember here, it's a complex exponential, so the direction of rotation is also decided. Right? So either if it's positive omega, it's in the anti-clockwise direction. If it's negative omega, it's in the clockwise direction. So one must not forget that here we are talking about a rotating complex number or a function obtained from a rotating complex number, and the direction of rotation is also important. Yeah. Now, what is this statement saying? This statement is saying something like what we know from basic physics. It's saying that if I resolve an agent, for example, a force or a torque, whatever it is, depending on the situation. If I resolve an agent into its components along directions where I can interpret the response. So, for example, suppose I have a force acting on a body, and if I can resolve the force into its x, y and z components, let's say in 3 dimensions, and I know what will happen to the body with a force in the x direction, I know what will happen to the body with a force in the y direction and z direction, then if the system is linear, then I can look at the response of the system to the force in the x direction, look at the response to the force in the y direction, the force in the z direction, and I can linearly combine these in the same way. That's exactly what we are saying here. We are saying that you can think of the periodic function as resolved into its many components along the directions k omega naught, right, for k going from minus infinity to plus infinity. So each of the integers k gives you a different direction, so to speak, and there is a countable number of directions. Now, in each direction, you know what the system does. I mean, what the system does to the frequency omega is to multiply the component in that along omega equal to, see, this is equivalent to saying omega is equal to k omega naught here. This is equivalent to saying omega is equal to k omega naught here. So, to an excitation of the form e raised to the power j k omega naught t, the response is h omega evaluated at k omega naught. So, h k omega naught e raised to the power j k omega naught t. And therefore, since the system is linear, one may add up all these responses to get a composite response as we have shown here. That is the statement that we are making. So, it is very important that we learn to interpret the same expression from various perspectives, because different perspectives are important in different circumstances, right. Different perspectives give us a different insight in different circumstances. So, that is one of the important things in a course on signals and systems. It is very important that we learn to see that the same equation has many meanings, tells us a great deal when we interpret it from different angles. Now, you see, let us ask the question. Suppose we don't want to confine ourselves to the context of periodic functions or to the context of functions that are restricted in time. Then how do we take care of this idea of using the Fourier series, or can we generalize the Fourier series to take care of that situation? Well, one way is to see whether you can think of that situation as an extension of this one. So, suppose you visualize a function which is limited in time, but then you visualize that interval growing without bounds. So, function that, if you wish, is restricted between 0 and t can be assumed, or maybe minus t by 2 and plus t by 2, can be slowly assumed to grow in its bound, or you can think of t as growing, and you can visualize a consequent effect on the fundamental frequency. What have we said? You see, as I said again, let us reinterpret the equation that we have written here again from a different perspective now. What have we said? We have said in this equation, or we have said in the Fourier series representation, that if you have a function that is periodic with a period t, for a reasonable class of functions, I could think of the function xt as a linear combination of e raised to the power j k omega naught t, where omega naught is 2 pi by t. So, now I am emphasizing the 2 pi by t part. It depends on what you emphasize. So, now I am emphasizing the 2 pi by t part. Now, if I take t tending to infinity, that means if I allow the interval to grow without bound, then I am what I am doing effectively is to accommodate all possible functions which are defined over a complete interval from minus infinity to plus infinity. And then what is happening to the fundamental frequency in that case? In that case, the fundamental frequency omega naught tends towards 0. 2 pi by t tends towards 0. Another way of understanding this is, if I look at, if I think of omega itself as an axis, if I think of sorry, omega itself as an axis, then what I have been saying so far is something like saying that I need the following points on the axis. I need the point 0, I need the point omega naught, I need the point 2 omega naught, and so on, all integer multiples on this side, and I need the point minus omega naught, minus 2 omega naught, and all the integer multiples on this side. Now, what are we saying from this perspective? When I put omega naught equal to 2 pi by t and take the limit as t tends to infinity, what is the effect on this? The effect on this is to bring these points closer and closer together. All right? And then in the limit, of course, there again there is a catch. You see, just as we move from discrete to continuous. That is what we are doing here. As we take t tending to infinity, we are going from discrete to continuous. And we have to be careful in the way we modify the operations. So, here we have a summation, right? As we make t tend to infinity, instead of a summation on the k, it is going to move towards an integration. And when we move from a summation to an integration, we need to do some work. We will come to that later. Actually, at the moment, we will first develop the idea informally, and then we will fill up the small gaps that might be left. Yeah. So, right now the idea is that we recognize that as t tends to infinity, we need to bring these points arbitrarily close, and therefore, instead of a summation, you will have the continuous omega axis coming into the picture. So, instead of an expression like this, we need to have an expression like this. Something, we will have to put something here. We we need to have an expression like this. Now, we need to fill in this gap here. What is this gap? Now, here, what is the corresponding term here? The corresponding term here is a component of the function xt along the direction k omega naught, right? What would appear here? Similarly, a component of the function xt along the direction omega, and omega is now continuous, right? And if we go by our experience of the impulse response, we know how to obtain the component of a continuous function ht along the direction omega, right? If we go by our experience of the impulse response, we know how to obtain this component. So, we knew that for ht we had h omega described by integral ht e raised to the power minus j omega t dt. Yeah. So, therefore, for xt also, the input xt, if it is not periodic, expect that there would be a similar quantity, let us call it x omega, given by xt e raised to the power minus j omega t dt. So, this is a projection of xt in the direction omega, or along the function, along the vector e raised to the power j omega t for each omega. It is a function of omega. So, what we expect is that in this expression x omega would come in. So, we expect that x omega would come in here. What is the statement that we are making here? We are saying we can reconstruct a vector, think of xt as a vector. We can reconstruct a vector xt from its components along the different directions omega by taking a linear combination of the component multiplied by a vector in that direction. Now, I need to correct myself here, not a vector but a unit vector. So, I may need to have a constant here. I may need to have a constant. Why do I need to have this constant? Because I need a unit vector, a component times the unit vector in that direction added up over all the vectors. So, to make it a unit vector, I may need to have a constant, right? Now, at this point in time, I shall straight away state the constant. I shall not prove it. It is not very difficult to prove the value of the constant. It is just tedious, and therefore, if some of you are interested, we might certainly go over the proof as to why the constant, or indicate why that constant should be what it is. But on the other hand, if it is not critical to the whole discussion, we may simply accept the constant as it stands. So, in fact, it turns out that the constant is 1 by 2 pi. This 1 by 2 pi allows you to make this a unit vector. Or another way of saying it is, just as we did in the case of the Fourier series, if you remember, we said to make it a unit vector, you may have to introduce a constant on the analysis side and also on the synthesis side. But we will introduce a constant only on the synthesis side to take care of both the constants. That is what I am doing here. So, we will introduce a constant 1 by 2 pi only on the synthesis side, right? And this shall give us x of t. Yeah, this gives us x of t. let us pay attention to these equations. Let us look at these equations in great detail once again. Let us spend some time on interpreting each of these equations once again. Firstly, what is this equation? This equation takes us from xt to x of omega. Now, please note that the t-axis is continuous and runs over the whole real axis. The omega axis is also continuous and runs over the whole real axis. Right? What does this equation do? It takes us back from x omega to xt. Right? Again, the t and omega axis are both continuous and occupy the whole real axis, or take on all possible real values. Now, what is the statement that we are making here in this equation? The statement that we are making in that equation is, just as you can represent xt in time, which is the most natural way to represent it. I mean, you can express a function in terms of its natural independent variable. So, if it is a time function, it is most natural to express it in terms of time. Similarly, you may also choose a different independent variable and express this function totally in terms of that new independent variable, which in this case happens to be the variable omega, the frequency. And it is valid to express the function in terms of a new independent variable if you can go back to the original function completely from that new representation. So, it means if I see, this is a forward, or this is an analysis equation. Analysis means, see, the word actually, you know what the word analyze means? The word analyze actually means to break up, or to to separate, to decompose. That is what we are doing here. We are decomposing the function xt into its components along different directions, e raised to the power j omega t. And the word synthesize, syn means to bring together. Synthesize means to bring together and construct, or to bring together and recapture. And that is what we are doing here. We are synthesizing xt from its components. Right? We are synthesizing xt from its components along different directions, e raised to the power j omega t. Now, one more, let us keep looking at various aspects of the equation. So, the next aspect that we need to emphasize is, what is the vectorial interpretation of this equation? I am repeating it because it is important for this to really sink in very thoroughly. So, the vectorial interpretation of this operation is that you are taking the dot product of xt with e raised to the power j omega t. And please remember, when you take the dot product, what do? You take the product of corresponding components. See, the thing is, you may think of each point t as a different component. Take the product of corresponding components and add over all the components. Now, since the components are continuous, you integrate instead of adding. Is that right? Since the components are a continuum, it's a continuum of components, you integrate instead of adding. So, you are taking a product of corresponding. Now, when you take a product of corresponding components, we also explained last time why the second component must be complex conjugated. That is because if you wish to take the dot product of a function thought of as a vector with itself, it must give you the square of the magnitude. That will happen if you complex conjugate the second component, and therefore we complex conjugated e raised to the power j omega t. Right? So, this is in effect like the dot product. Now, of course, as I said, we should have taken a unit vector in that direction. So, there should have been a constant here, but what we did is we said we will require a constant there, and we will also require a constant in the synthesis equation. What we will do is we will put all that constant in the synthesis equation. So, this 1 by 2 pi which we have here takes care of the constant requirement here and the constant requirement here. So, that is the other interpretation. Now, so this equation is very, very clear in our minds. We have a vectorial interpretation to it. We have an interpretation in terms of going from one domain to another, right? And now we come to this equation. What does this equation do? It takes us back from the omega representation, from the frequency representation to the representation in time. Right? What are we saying in this equation? Vectorially we are saying take the component along the direction omega, multiply it by a unit vector. Now that unit business is being taken care of by the constant, right? Multiply it by a unit vector in the direction omega, and instead of adding, since it's a continuum of omegas, we integrate over all omega. Is that right? So we have integrated over all possible components omega, the component multiplied by unit vector in that direction. Right? This is very interesting. Now a third point of importance. This is a vectorial interpretation, it's a domain based interpretation, a third point of importance. Look at the equations themselves now. Look at the nature of the equations. You see, if you for the moment forget about the interpretation of t and omega, if you forget that t is time and omega is frequency, just think of them as two mathematical variables, both of which occupy the whole real axis. Here we have an equation going from the independent variable t to the independent variable omega. Here we have an equation going from the independent variable omega to the independent variable t. Now there is a great similarity between the two equations. Actually, if you look at this equation and this equation, they are almost identical. See, this 1 by 2 pi can be absorbed, or if you like, you can put 1 by square root of 2 pi here and 1 by square root of 2 pi there. It's just inconvenient to do, so we don't do that. But otherwise, you can put a 1 by square root of 2 pi on both the places, right? And in that case, the equations will become identical. See, if you just reverse the roles of omega and t here. So suppose you wrote capital X of t e raised to the power jt omega, dt is equal to x of omega. So I just reverse the roles of x and of t and omega here. The equations would look almost identical, except that you need a minus sign here. So if you write x of minus omega instead of x of omega, you get exactly. In fact, we'll make that statement precise. So what I'm trying to point out is that there is a great symmetry between the two equations, the analysis equation and the synthesis equation. Now this symmetry we had not had before. When we looked at the Fourier series, we didn't have a symmetry. That's quite natural, because in the Fourier series, you're moving from a continuous function to a discrete representation. You're coming back from a discrete representation to a continuous function. So naturally, symmetry is not expected. But here you're going from a continuous function to a continuous representation, and from a continuous representation back to a continuous function. So it's not surprising that you have some kind of symmetry. It's a very, very powerful kind of symmetry. In fact, now we shall give these relationships a name. Right? We'll give them a name. This relationship, which takes you from xt to x omega, is called the Fourier transform. This is the Fourier transform relation. And naturally, since this is the Fourier transform, this would be called the inverse Fourier transform relation. This is the Fourier transform of xt. So we say the correct statement or the complete statement is, this is the Fourier transform xt of xt to give you capital X of omega. The Fourier transform of small x of t is capital X of omega. That's a complete statement. And this is a statement that the inverse Fourier transform of capital X of omega is small x of t, right? And we shall use a succinct or a shorthand notation for this. We will say xt has the Fourier transform. We will write script f. In future, we shall use script f to denote the Fourier transform. Script f, capital X of omega. And similarly, we shall say that capital X of omega has the inverse Fourier transform. So, we will write script f inverse given by xt. Yeah. All right. So, script f Fourier transform, script f inverse, inverse Fourier transform. Now, you must look at these equations very carefully. They shall occur in your study of electrical engineering or in a study of most systems very, very frequently, right. So, it's a good idea to get a thorough familiarity with what these equations mean and how they are to be used, right. We shall use them again and again to get a better understanding, but at this point in time too, one must get a thorough understanding both of the interpretation and the form. It's as, see, the interpretation we have said, but it's, to get used to the form of the equation. Form of the equation means the precise way in which the equation is written is also equally important. And if one understands the interpretation, then remembering the form is not difficult, right. If one understands the equation or the interpretation, then remembering the form is not difficult. Yeah. So now what we'll do is we've looked at these equations carefully. I shall erase them. And we shall make another statement about consequence. You see, xt has the Fourier transform capital X of omega. The impulse response ht has the Fourier transform. If you look at it, h omega is the Fourier transform of ht, right? H of omega. Now, I must again emphasize that the Fourier transform may not exist for all functions, because this integral, being an infinite integral, may not converge. But again, as I said, let us talk positive first and then talk negative. So, first let us confine our attention, let us assume that we are looking at that class of xt's, ht's and so on, which has a Fourier transform, right. So, let us talk positive first, then we will talk negative. We will say, oh, but it's this class of functions that has a Fourier transform, and in fact that will lead us to a different subject in signals and systems later. At the moment, let us focus our attention where a Fourier transform exists. Now, suppose the Fourier transform of the output also exists. Suppose we pass xt into an LSI system with impulse response ht to get yt, and assume that transform of xt, ht and yt all exist. Then what do you think we can say about the Fourier transform of yt in terms of the Fourier transform of xt and Fourier transform of ht? Well, I will give you a hint. You see, if you looked at the Fourier series representation, what did you say? You said, if I find the component along the direction e raised to the power jk omega naught t, the component along e raised to the power jk omega naught t at the output could be obtained by multiplying the input component along e raised to, or multiplying the input component at k omega naught t by the impulse response component at k omega naught. It's a decoupled relationship. isn't it? It's decoupled in the sense that the effect seen at a point omega on the frequency axis relates, I mean at the output, the effect seen at a point omega on the frequency axis at the output relates only to the corresponding contribution from the input and the corresponding contribution from the impulse response at omega. It does not bring in other omegas. What is this in the language of systems? If you remember, we have defined so many different properties of systems. Yes, that is right. Right. So, this is the property of memoryless systems. Right. Can you see that? We are saying that from a system which possibly might have memory, we are going to a system which behaves in a memoryless manner on the new independent variable. Right? Well, what we are saying actually is something much stronger than just memorylessness. We are saying that y omega is equal to h omega times x omega. It's a statement slightly stronger than memorylessness. It's also a statement of linearity. It's a linear, see, now what I'm trying to say is the following. Think of this as a system defined on omega. Think of omega as an independent variable. So you have an input defined on omega, the output is also defined on omega. Now, this is an example, if you remember, if you think of omega as an independent variable, this is an example of a linear memoryless system. Right? So, not only is it memoryless, it is linear as well. Right? It is linear because if you take, if you think of it as a system defined on omega now, with the independent variable as omega, right? Then if you have x1 resulting in y1 and x2 resulting in y2, then k times x1 plus L times x2 will indeed result in k times y1 plus L times y2. That is very easy to show. And of course, it is very clear the system is memoryless. So, in the next lecture, we shall begin first by re-justifying this formula. We have come to this conclusion by extending our idea from the Fourier series representation, right? We said, oh, in the Fourier series, there is a component-wise product. So, we can extend it to the Fourier transform. But we should prove it formally. So, we will begin by proving this formally first, and we shall also then take this interpretation further. So, you see, we have the notion of a transform here, a Fourier transform, which takes you from one independent variable to another independent variable. We would like to understand in a little more depth what we mean by transforms. See, so far we have looked at signals, we have looked at systems. Now we are coming to transforms. We shall see that transforms is the next level in the hierarchy. Signals was one level, a mapping from signals to signals is a system, and transforms shall be one level higher in a certain sense, right? So, with this we conclude today's lecture and proceed the next. Because